All right, we're going to start our next section and covering vector functions and space curves a little bit. And what we mean by a vector function, let me just put one, or kind of give the definition here. A vector function is a vector made up of functions, just like the name suggests there. And so it'll just be a three-dimensional vector that if we drew the curve out where x equals f of t, y equals g of t, and then z equals h of t on our three-dimensional graph here, let's just say it starts here on the x-axis and then just kind of winds up three-dimensional, something like that. The r of t then is the vector that has the endpoint at whatever the x, y, z is. That's our particular t value, parameter or time, I guess most often what we think of it as. And so we just make a vector out of the functions here. And that's phrased as a vector function. And so one in particular here, let's just say r of t equals t, 2t, 3t. So what does that look like? Well, if you just think about the curve here, you got x equals t, y equals 2t, z equals 3t. What is that going to be? That's just a line, okay. And it goes through 0, 0, 0. Right? T equals 0 at 0, 0, 0. And the other thing we need about a line, of course, is the vector. And our direction vector, if you will, we could just use t equals 1, so it's would be direction vector 1, 2, 3. So it goes through 0, 0, 0, x equals 1, y equals 2, z equals 3. So it kind of comes out like that, right? Kind of hard to draw. But that's our line, and so the vector then would be all the vectors that for each particular t value would make up that particular function. So anyway, that's what it looks like. Now here's another interesting one. Talk about drawing it. So r of t equals cosine t, sine t, t. Make that our vector function. And so let's sketch it out. Of course, here the x value would be cosine t, y value sine t, z value t. All right. A little different. If you just look at the xy plane, the xy, so you just kind of look at it from above. Well, if you just look at it, from our normal thinking here with the z value pointed up and then the x and y value like that. If you just think about it from above, we're just looking at the xy plane, and so you got x equals cosine t, y equals sine t. And so what does that? Yeah, that's your circle. That's right. So the x and y values, yeah, you just get the unit circle there. And so the t value, what that adds to it is it just makes it climb, right?
Okay, yeah.
So at, at 0, 0, yeah, you still got this point, x is 1, y is 0. Let me make it a little bigger than. So then the next value, we circle on around. The y value is 1, x value 0. But it just starts climbing up a little bit, and so you, instead of being on the xy or the y-axis, it's up here at whatever time value that would be, which I guess that would be pi over 2. If you want to think about it that way. Anyway, it just makes it climb. Yes, so it just starts climbing with the z, and so it just kind of loops around and does this. The way the book, and then it kind of loops around backwards like that. The way the book describes it is just it's a helix, and you've got these points are on the outskirts of a cylinder. Think of a cylinder overlaid here. That's just kind of winding its way around, depending upon time t. Make sense? So anyway, you get some interesting drawings. So this would, and the book has a much better picture than I can draw. My drawing skills aren't terribly accurate there, but just kind of get the general idea. It's just kind of looping around. Like I said, it calls it that's a helix in shape terms. All right. So we got a couple of those. Just kind of think about what it looks like. Maybe look at it in 2 dimensions, what it would look like in just the 2 dimensions, and then add in the third one to see what you get there. All right. Now, of course, what we need to do is do our normal calculus things, limit, derivative, integrals of these functions. And the good news is, mostly, they will be very analogous to their 2-dimensional counterparts. And the limit of a vector function is, there's no big surprises here. If you do the limit as t approaches a number a, or value a, of a vector function, then the good news is you just do the limit of each component part. Limit of t approaching a of f of t. Then you do the limit as t approaches a of g of t. Limit as t approaches a of h of t.
I could see they would have had to prove this, right? But then once they're done this, the derivatives.
Yes. Yes, it is. Mm-hmm. Yep, follows right from all this. So what's the limit as t approaches 0 of r of t, where r of t is 1 plus t cubed, t e to the t times e to the minus t, and then sine of t over t. Just main thing here, just to remind you of a few of our limit rules. E to the negative t, yeah. All right, so the limit, t approaches 0, r of t here. Well, you take the limit of that, which that's easy. T approaches 0, that's just 1 plus 0. Be 1. The limit of that, you got 0 times e to the minus 0 times 1, yeah. That's 0. And this one's 0 over 0, isn't it? And so we have to use good old L'Hopital, right? So that would be the limit as t approaches 0 of the derivatives. So that would be cosine t over 1, which that's going to make it 1, 0, and 1. And so you wind up with the limit of this vector as the vector 1, 0, 1 as t approaches 0. All right, so no big revelations there, I guess. All right, so what about derivatives and vector functions? Well, again, just to remind you of a few things. If we do the derivative of the vector function, which we can also designate the vector of r prime, the definition is just like before. It's the limit as h approaches 0 Yep. Just do r of t plus h minus r of t, divide that by h. So just like for regular functions, for vector functions, still the same derivative. And the meaning of it still has the same meaning. What would r prime of t represent? Be the tangent, right? Be a tangent vector of r at whatever point P we are describing there. And then, of course, that's a tangent vector, and so, a lot of times we're looking for a tangent line, and so the tangent line, by definition, would be the line parallel to the tangent vector through point P, right? They also talk about the unit tangent vector, and they'll designate that as T prime. And just like all other times, to find the unit tangent vector, you just take the vector itself and do what? If I just want a tangent vector that's 1 unit long, divide it by the magnitude, yeah. So same drill, r prime divided by the magnitude. All right.
So
Question.
once we're done with derivative of it,
Mm-hmm.
it may be another curve, right? And you'll have to do sketch.
Well, the tangent vector is going to be it'll be linear line. Yeah.
Okay. Because I figured if you had.
Now the function itself, I mean, at each particular point. But I see what you're saying. Yeah, the actual vector itself could be a different curve, but you know, at each individual point, you got one straight line. Yeah, but yeah, I see what you're saying. That this may be a different shape if you graph the.
Graph the entire tangent. Right?
Yes.
I guess now we just need linear tangent. For the
Yeah, we'll just find the tangent line. Although we will talk about the second derivative here in a second too, I think. All right. Well, you know, that's our definition. I don't think they make us go through finding these derivatives by the limit definition, because it turns out if our vector function of t is f of t, g of t, h of t, good news is r prime of t is the derivatives, f prime of t, g prime of t, h prime of t. So, as we would hope,
It's just now we've got delta x, delta y, delta t, or z.
yeah. All right. So let's see. So for r prime of t equals 1 plus t cubed, t e to the minus t, sine of 2t, find the derivative vector. Again, mainly here just gets back in the swing of doing derivatives, I guess. R prime of t would be the vector then. What's the derivative of that? 3t squared. Product rule for the second part. I do it first times the derivative of the second. Should be negative e to the minus t, right? Plus the second times the derivative of the first, which would just be 1. And then the third component would just be chain rule, right? Derivative of sine is cosine, so it would be cosine of 2t times then the derivative of the inside. So it would be 2 cosine t. So that's 3t squared. Negative t e to the minus t plus e to the minus t, or factor out the e to the minus t, I guess. They might do that. And then 2 cosine 2t, the last component. All right, then part 2 of that. Let's find the unit tangent vector at the point where t equals 0. Just remember, on the unit tangent vector, you got to divide by the vector length. All right, so first of all, r prime of 0 we would need derivative at 0, so that would be 0. Vector be 0. 0 plus 1, so that would be 1. And then 2 times the cosine of 0, so that would be 2. Plug in 0. And so then the tangent vector at 0, we take the r prime at 0 and divide by the unit. The length. And so we take that 0, 1, 2, and then divide that by the length there, which would be 0 squared plus 1 squared plus 2 squared. So that's 5, yeah. So 0, 1 over square root of 5, 2 square root of 5. And yeah, I don't know how they'll exactly... yeah, I think they would. I think they don't care as much about the denominator being a square root. So, matter of fact, they might even leave it factored out like this. Could leave it like that, but